All right, we're looking at class 4.5. The first thing we have to do is we need to copy over our trajectory from last class. So if you look at last class, the trajectory I'm referring to is right here. So let's copy that down. We see the x component is constant, 20.8 meters per second, and we have the y component there, which is changing. So let's sketch that out. I'm going to just zoom in a little bit. All right, so here's my initial position. Ball has a parabolic trajectory, max height, and then it lands somewhere over here. This should be symmetric in shape. This is its final position. Our x component is constant, 20.8 meters per second. Let me draw it at the top as well. 20.8 meters per second. 20.8 meters per second. It's really important to understand that the horizontal component of the velocity for any projectile is not going to change. The vertical component does change though because there's gravity in the vertical direction. So we saw last class that this one started with an initial vertical velocity of 12 meters per second. At the top, the vertical velocity is 0. And when it lands, there is symmetry here. So let me see if I can make a straight line straight down. That's going to have to be negative 12 meters per second. So as the ball travels through the air, how does Vx differ from Vy? Vx is constant. Vy changes. Specifically, it decreases on the way up and increases on the way down. Now, there's an interesting question about what should I label the final position. I'm just going to label the final position where it lands, but we'll see later on, sometimes we want to make the final position at the max height, like we do when we're trying to figure out what's the max height an object reaches. This is a nice graphic that shows how the x component remains constant as a projectile goes through the air, but the y component of velocity changes due to gravity. See how it mentions at the top the y component is 0, and then as it comes back down, the y component increases. We have a simulation here we can check out. I'm going to start with, I guess this simulation should be fine. If I have a projectile here at an angle, let's just make it 30 degrees. Let's make it just like this, like we have, 24 meters per second. Look, notice the velocity vectors here as I fire it. I don't want the total velocity, I want the vectors. We'll zoom out a little bit. So I'm going to do this in slow motion, but notice as I fire it, how the x component of velocity remains constant, while the y component decreases on the way up and increases on the way down. Just one more time. Notice the y component is getting smaller on the way up and bigger on the way down, and hits 0 at the top. So give this question a quick read and see if you can answer it on your own. So you know a couple things. The first thing you know is that Vx is constant. Therefore, Vx is still equal to 40 meters per second. It does not change. So I can eliminate choices 3 and 4. So my question is, what's the velocity value of Vy? Well, we know Vy has to change. So we know it can't be 30. So we know it has to be choice 1. Now, how could you prove mathematically that it's choice 1? You could use the equation Vfy equals V initial y plus a t, where Vfy is your unknown, V initial y is 30, the acceleration is negative 9.81 meters per second squared, and the time is going to be 2 seconds. Vf in this case would be approximately, not exactly, but very close to 10 meters per second. positive because it's still going up at that point. It hasn't reached its max height yet. All right, so here is the question from yesterday. We're actually going to solve for all these values now. We are going to solve for the time to the apex, the maximum height, the total time in the air, and the horizontal range. All right, so we're going to use the whole page here, but I'm going to start with my XY chart, just a really helpful tool for this unit for just keeping everything organized. I'm not going to combine any of my boxes just because I want to draw this a little bit quicker. It's an A. Let me just fix that. That's an A. Okay. So we know from yesterday's class, or Friday's class, or Thursday's class, that our initial velocity in the x direction is 20.8 meters per second. And that's what the final is as well, because it doesn't change. We also found that the initial velocity in the y direction was 12 meters per second. The acceleration in the y is always going to be, for any projectile, horizontal, angled, anything, negative 9.81 meters per second squared, and the x direction is going to be 0. So notice, this is our game of Sudoku, if you will, that we're almost done here. All right, we have like half the boxes filled. So let's answer the questions in the order they were asked. So the first thing we're going to do is look for time to the apex. So there is one other piece of information here that I'm going to add in. I like to, for any projectile question, I like to pretend that the problem stops at the top. So I gain a given doing that. I get a final value, for the final velocity rather, of 0 meters per second at the apex. Apex is another word for max height. So now that we have that, we can easily find the time to the apex. So in the y direction, I have 3 givens and 1 unknown. So I'm going to use the equation VF equals VI plus AT. I know I should use that one because I don't have D. This is the only equation that does not have D in it. So we have 0 equals 12 plus negative 9.81 T. We get 1.22. And that was actually the time to the apex we got the other day when we threw an object straight up with a velocity of 12 meters per second. So notice how it's basically the same thing because I'm completely ignoring the x direction. So I have my time to apex. Another thing I have as well is my total time. So I'm going to call it, this will be T apex. And I know T total is going to be 2.44 seconds. All right, now I want to find my max height. Now I can do this without using my time. And just in case I made an error with my time calculation, I'm going to stay away from using that. So let's look for max height. So let's not use time, so we only have one equation. Remember, I'm only using values in my y column right now because max height is at y distance. So we have 0 equals 12 squared plus 2, negative 9.81, D. Solving for D, we should get what we got the other day. We get a distance of 7.34 meters. So that's my max height. So that's going to go in here, 7.34 meters. Now we have the hang time. The only thing we need is the horizontal range. So there is something I'm going to do right now. It might be a little bit confusing. It's not perfect, but it kind of shows that the XY chart, while it's a good tool, is not perfect. In order to find the horizontal range, the ball goes up and the ball comes back down. So I cannot use a time of 1.22 seconds to get my horizontal range. I have to use the total time of flight. So where do I put that in my chart? Just bear with me here. What I'm going to do is I'm going to put the total time of flight into my X column. So this will be 2.44 seconds. Now, does this mean the time is different for the x and the y? No, not really. It's just that in order to calculate the maximum height in the y direction, I use half the time because that's how long it takes to get to the max height. In order to get the maximum distance in the x direction, I use the total time because it's going up and down. So I need the total time of flight. So to get the horizontal distance, I'm just going to scroll down a little bit. Sometimes we just call that range. So I'll call it horizontal range. We're going to use the equation d equals VIT plus 1/2 AT squared. D equals, again, now we're only using our horizontal givens. So we have 20.8 times 2.44 plus 1/2. The acceleration x direction is 0. This is 2.44 squared. This whole term goes away. And now we can get our horizontal distance. $50.8 approximately. Now, if I were to use accidentally the 1.22 seconds, I would only get half the distance. I would get how far it traveled horizontally as it reached its max height. So just to show you what these values would look like up on this picture here, the horizontal range would be this distance here. This would be 50.8 meters. The max height here would be 7.34 meters. So I could actually do this in that simulation that I showed you earlier. If I show you here, let's see, I actually did 24 meters per second at an angle of 30 degrees, but I think I was accidentally up 1 meter. So let me reset it real quick. Let's go down to ground level, 30 degrees. And if I fire it, I'm gonna have to zoom out a little bit. I can use this measuring tool to measure everything. So let's see the max height, 7.34. Notice the range at that point is 25.4, half the total range. Look at the time to the max height. That's what we calculated as well. Total time of flight, 2.45, because they didn't round. And their horizontal range is 50.8. So pretty much exactly what we got. We just rounded ever so slightly. So that wraps up here. You don't have to do those extra practice questions there. Now, class 4.6 is what you will be ultimately submitting. Notice here how I gave you the answers to 1 and 2A and B. So please make sure you do these on your own time and make sure you're able to get the correct answers. All right, if you need extra, or if you need help, I'll be available in the mornings on the virtual classroom link. All right, you could also ask each other for help if you need it. All right, so please make sure you were able to answer these questions and show work. You are going to submit this. You're going to submit this whole piece of paper, front and back. So please make sure you're able to do these and show work for it. Do you need an XY chart? I think it would be a good idea to get in the habit of using one. You don't really need one, but I think it would be very, very good for you to get in the habit of using one. It's a great tool to be used to using. The last little bit for this unit that we're going to discuss are two things: the effects of air resistance and some optimal angles. But let's look at the effects of air resistance first. So let's go back to that simulation. So if we go to the simulation, notice how far the ball went. If I turn it on air resistance, notice what happens a little bit differently. Look at the height it reached and look at the horizontal range. They were both significantly lower. So how does air resistance affect the max height reached by a projectile? With air resistance, it does not go as high. And with air resistance, it does not go as far. And the last one here, how is the direction of the drag force on a projectile similar to the direction of the force of friction on an object? Well, what do we know about the force of friction that acts on an object? Which way does it always point? It always points opposite motion. Let's see if drag force does the same thing. So I'm going to go to the drag simulation because that one makes it a little easier to see the drag force. I'm going to click on force vectors here, and we're going to fire a projectile. All right, I'm going to go in slow motion so you can see it. Notice the force of drag vector right here. Notice how it's always pointing opposite the direction of motion. So it's just like friction. And it is a type of friction specifically. So this last bit here is fairly intuitive. It's about how launch angles affect things like max height, time of flight, v initial y, and vx. So let's go back to our simulation here. We'll just go to the intro. We'll clear the screen. Bring this back down. So if I fire it at 25 degrees, it goes a certain distance. Now, if I increase that angle, notice the ball goes higher. If I increase that more, the ball goes even higher. And if I increase it to 90, it goes even higher. So as the launch angle gets closer to 90 degrees, the max height increases, as does the time of flight. Think about this. If you want a ball to be in the air as long as possible, to go as high as you want it to go, which way are you going to throw it? You're going to throw it straight upward. This will also increase v initial. V initial y will increase, but vx will decrease. Now, why is that? Just if I sketch it out without doing any math, think about if I have a velocity vector like this. Notice how vx is really big and vy is really small. But if I take that same vector and I just angle it upward now, notice how vx got significantly shorter, but vy got way bigger. Now, as we go back the other way, as we get closer to 0, the ball will not go as high. The max height is going to go down. If I fire it at a lower angle, the ball will not go as high. If I lower it really low, it does not go as high as it did when it was at 90. It will not be in the air as long. As we saw here, it's going to be the exact opposite. V initial y is going to go down, but Vx is going to get bigger. So I'm just going to make a little point here, closer to 0. It's going to be closer to 90. But there's only two things that affect the range, the horizontal range of a projectile. If you think about the equation we used in class 4.5, we used the equation d equals VIT plus 1/2 AT squared. AX is 0, so this whole term goes away. So the only things that it depends on, dx is equal to our velocity in the x direction times our time. So the only two things that matter are Vx and t. Well, look at these two situations. If I make the angle bigger, I increase time of flight, but I decrease Vx. If I make the angle smaller, I decrease the time of flight, but I increase Vx. So what would be the optimal angle to fire something at for the greatest horizontal range? That would be 45 degrees. That's a question that gets asked a lot on the exam, so please be aware of that. Just something you kind of have to memorize. It sort of makes sense. It's like the Goldilocks between the two. You're trying to optimize time of flight while also trying to optimize your horizontal component of velocity. But keep in mind, that's just for greatest horizontal range. For greatest height, it would be 90 degrees. For greatest time of flight, it would be 90 degrees. Now, one last point. It doesn't really show up on the Regents exam, but I think it's something that's important to note. Complementary launch angles. So if I clear my screen again, by the way, all these things only hold true if you are at ground level, fired from ground level. If I fire something at 25 degrees, it goes a certain distance. If I fire it at the complement to 25 degrees, which would be, I believe, 65 degrees, notice where it landed. Complementary launch angles have equal horizontal ranges when fired from ground level. They have equal horizontal ranges. All right, so that's it. So the only thing you have to do for today is make sure you do this front page here. I gave you the answers. You just have to show the work to get to the right answers and make sure you submit that. If you have any questions, make sure you pop into the virtual Google Meet office hours.